Our next speaker is Brad Chamberlain. Brad is a principal engineer at Cray, where he works on parallel programming models, focusing primarily on the design and implementation of the Chapel parallel language in his role as technical lead for the project. Brad received his PhD in computer science and engineering from the University of Washington in 2001, where his work focused on design and implementation of the ZPL parallel array language, particularly on implementing and generalizing its region concept. Brad here is going to talk to us today about Chapel.
Thanks, Amanda. Am I on? Yeah? Okay. So thanks very much, everybody, for coming this morning. Again, my name is Brad Chamberlain. So one of the casualties of us switching from the two-track to the one-track format is I had about 30 minutes worth of jokes, which I've had to completely cut out of my talk. So that's the only one that survived, and it's all downhill from here. So scalability, I work for Cray Inc., and scalability is obviously a crucial part of Cray's business. We build large machines. We want to allow our users to get high performance on these large machines, and scalability is obviously crucial for that. My specific job at Cray is that I want to help enable our users to program our machines more productively, and I do that through innovation in language design. So in particular, I'm working on this language called Chapel, which I'll be telling you about today. And for the purposes of my work, we define productivity as a combination of performance, plus programmability, plus portability, plus robustness. So that's what we're trying to do today. This is kind of the thesis of my talk, and I'll spend a lot of time sort of defending this thesis, and then I'll come back to it, because it'll probably make more sense the second time around. If you look at the way people program HPC machines today, I sort of hold that there are three main limiters to scalability. The first is that most of the models we use today have very restricted programming and execution models. And the single program multiple data, or SPMD programming model, which you'll hear more about in a bit, is one of the big factors here. The second is that our programming models tend to expose a lot of the low-level implementation mechanisms up to the user. And the third is just a general lack of programmability. And I define this as not only the ability to write code, but also to read it, to modify it, tune it, maintain it, experiment with it, sort of all the things you do with a piece of software over its life cycle. In the mainstream software engineering industry, these are very important. In HPC, they tend to be sort of ignored a lot more, I think. So as I said, we're working on this language called Chapel. It's a new parallel language we're developing at Cray. There are sort of five main themes that drive our design. The first is we want to be a language that supports general parallel programming. So I think of this as if you have a parallel problem you want to write up, you should be able to write it up in Chapel. There shouldn't be a point where you say, well, I've kind of run into Chapel's limitations, and now I'm going to switch back to the old way that I used to program. So we think of this general parallel programming as being support for data parallelism, task parallelism, and then arbitrary nesting of those types of parallelism within one another. We want to be able to sort of express parallelism at general levels of software, so executable level, function level, iteration level, statement level parallelism, and also to target general levels of hardware parallelism, so across nodes, across cores within a node, parallelism within a core if you have that capability. The second theme in our design is to reduce the gap between mainstream programming languages and parallel programming languages. So most students are coming out of school today probably learning something like Java or maybe C#, Perl, MATLAB. And then if they join the HPC community, we sort of put them through this hazing ritual where we say, well, we program in Fortran and MPI, welcome to the family. And I think there's sort of this sense of, they've been teleported back 20, 30, 40 years and don't understand what's happened exactly. So we want to fix that, and at the same time, we want to not sort of ostracize traditional HPC programmers. We don't want to come up with a model that a C or Fortran programmer would look at and say, well, I have no idea how to use this because I just have never really programmed in anything like Java, for example. And then these last three themes I'll talk about more in my talk, so I'm not going to really define them here. But the first is we want to have support for global view abstractions. The second is we want to have control over locality in the program. And the third is we want what we call a multi-resolution design to the language. Again, I'll define those as I go. So here's the way my talk goes. There's some gray text up there which isn't showing up, which says I've just given you the motivation for Chapel. Next, I'm going to talk a little bit about this notion of a global view programming model, what it means, and how it plays into scalability. I'm going to give you a brief language overview. And I'll probably have to skip through some of that material at high level, but I'll make it available to you afterwards to look through. And then I'll do some wrap up at the end. And in particular, try to tie Chapel into the question of whether or not it would be appropriate for more of a data center style programming model, given sort of that we're here at the Google conference. Okay, so what do I mean by this term global view? Let me just start by taking a very simple problem. This is probably one of the simplest, interesting parallel codes you could write. You want to apply a 3-point stencil to a vector. So in particular, I want to take this blue vector and sort of maybe take the average of each element's 2 nearest neighbors and assign them to the interior portions of my yellow vector here. And I would say that if I describe this problem to you, mentally the image you'd probably get in your head is this thing on the left, and that represents the global view of the problem the way we think about it. Now the way people program this in practice today is using what we call a fragmented model. And the distinction here is that when you're programming your code, you're thinking about what one process or what one thread does. You're not thinking about the problem as a whole. So the sort of logical average of these 2 vectors gets fragmented, essentially. So the way that this tends to work is, let's say I'm running on 3 processors, indicated by these red bars here. I'm going to take my vectors and first of all chop them up so that each processor owns a piece of that vector. Then I typically, for these kind of stencil-style computations, I allocate a little bit of extra space to cache values from neighboring processors. I insert some communication to update those caches. And only at that point can I do the original computation I wanted to do, the averaging of the nearest neighbors. But of course, still I'm writing about that on a process-by-process basis, as opposed to sort of, again, at the conceptual global view. So let's look at some code to implement this. This is some code on the left that uses a global view model. And in fact, I think this is all legal chapel code. So I declare my problem size n to be 1,000, say. I declare 2 arrays a and b to be of size 1,000, where I allocate a floating point value for each element. Then I have a for all loop that iterates over the elements and does the averaging. Okay, so the main thing to note here is that I've done all this in terms of my global problem size n, global index space. Conceptually, the way the control flow here goes is I sort of have a single conceptual thread entering main. And then when I hit concepts in the language which create parallelism, like this for all loop, I'll get parallelism, and it'll conceptually contract back to a single thread at the end again. Okay, so in contrast, using the SPMD model, single program multiple data, which is one of the main fragmented models people use in practice, I would define my global problem size again, but then I would compute, well, what's the local portion that each processor owns? And so I'll take that global problem size and divide it by my number of processors. I'll then allocate my local arrays over that local size rather than the global size, again, adding 1 to get these neighboring values. I insert some communication, and then I have the loop at the bottom itself, which again, I'm expressing in terms of the local problem size. So there's a little bit more detail management that has to happen here, a little bit more complexity. And in fact, this is a little bit error prone. So the first time I wrote this code, I gave this talk 5 or 6 times, and finally a colleague said, you know, you've got a bug in your code there. There's a boundary condition on the sort of extreme processors in that bottom loop down there that you have to take care of. And so this purple code is sort of the fix for that. And these kind of problems tend to creep into these codes all the time. The other thing to note here is that the execution model is you've got sort of k threads entering main, executing the whole code, maybe taking different paths through control flow, but by and large you have this sort of single static amount of parallelism for your entire code in this programming model. One other note on this before I go on is that I've written this code sort of assuming that my problem size n divides evenly by my number of processors. I could write a more general version, but that would require more effort. And so in practice, people often make these kind of simplifying assumptions that make their code more brittle than it perhaps ought to be, just because it's easier. Okay, so this is that same code implemented in MPI, which is kind of the de facto standard for parallel programming today. It's pretty much the same thing we saw, just with more arguments and things to take care of the reality of the situation. The previous slide was more like a pseudocode implementation. So the main thing I want to point out here is that you could all learn this, you could all program in this, but we started with a pretty simple example here. And if we go to a higher dimensional array, say a 3D stencil rather than a 1D stencil, then the amount of communication you have to do expands geometrically. So this is an example from a benchmark called the NAS multigrid benchmark, or MG. It's a projection stencil where we take a weighted average of a 3 by 3 by 3 set of points, combine it down to one element. And if you program this up in Fortran plus MPI, it results in this code here. Again, lots of detail management, lots of sort of chopping up these arrays, doing the communication, so on and so forth. In Chapel, that code looks like this. Again, because of the fact that we're a global view language, we don't have to explicitly manage all of those details in line with the expression of the algorithm. That's taken care of by more advanced users and or the compiler and or the runtime. I'm not going to walk you through this code in detail. This being a scalability conference, you would of course like to see some results that sort of show that Chapel's amazingly scalable. The unfortunate truth is that this is very much a work in progress, and so I don't have those figures to show you today. However, the concepts that I'm showing you here, these distributed arrays, are based very heavily on our previous work in ZPL, which was sort of the data parallel subset of Chapel, essentially. And I do have results for that, so let me walk you through those before I get deeper into Chapel. So this is that same computation in ZPL. It's expressed a little bit differently. You can see the 27 points of the stencil here and the 4 weights of my cube over here. It's still concise compared to the Fortran plus MPI, but there are some differences from Chapel. And this is the speed up we got for the ZPL code. This is probably in the late 90s on a Cray T3E. So pretty small machine scale compared to what a lot of people are using today, but I think the lessons here still apply. Now this is a speed up graph, meaning that higher is better. This dotted line sort of represents ideal linear speed up, and the ZPL figures are in yellow and green. We had 2 different versions we were looking at, whereas the Fortran plus MPI is in the blue. So the nice thing here is not only was the ZPL code shorter, more readable, more maintainable, but it also performed better. And so why is that? The main reason that ZPL scales better in this case is running on the Cray T3E, using a message passing protocol like MPI is not the ideal way to communicate. It's a very portable way to communicate on a lot of different machines, but the Cray T3E had better ways to communicate using single-sided messaging called a SHMEM library. And because ZPL didn't express the semantics of what implementation mechanism you use for communication in the code, the compiler could map to SHMEM on the T3E, and then on a more generic cluster that only supported MPI could map to MPI and do sort of similarly to what you would expect for MPI. The other interesting thing is that ZPL actually performs better at the smaller scales as well. When you give new language talks, especially in the HPC community, people say, well, Fortran gets great performance, why would we ever want to use anything different? We're going to lose performance if we go to your language. And that's not necessarily true if you design your language well. I just want to point out that this result is a little bit old. There are other languages that have gotten similar kinds of results, showing that by taking communication semantics out of a language, you can get better scalability. I use this because I own the work, I guess. One other note here is that the ZPL program, again because of the global view expression of the computation, supports an arbitrary problem size which you can specify at runtime, arbitrary number of processors which you can specify at runtime, and you can use a 1D or 2D or 3D data decomposition dynamically. The MPI binary, for the kinds of simplifying assumption arguments I made at the beginning of the talk, assumes a power of 2 problem size, a power of 2 number of processors. Both those are specified statically. It always uses a 3D data decomposition. So it's a much bigger code. It's a much less dynamic code as well in terms of what you can do with it. Again, you could rewrite the code to relax those assumptions, but at what cost in performance, at what cost in development effort, in the fragility of your code, and so on and so forth. So this is sort of, again, summarizing the difference in code size here, and just, I guess I've made this point probably by now. The ZPL is shorter to a large extent because you don't have to put all this communication code in by hand. You don't have to do all this sort of manual bookkeeping of your arrays as you distribute them across multiple processors. And of course, code size is always a strange metric. My argument is not only is it shorter, it's also easier to write, read, maintain, and modify. Okay, just so to kind of summarize this introductory section, the advantages of a fragmented model like MPI are that it's a fairly straightforward model of execution. You could pick it up pretty easily if you're a computer science programmer. It's relatively easy to implement. You get reasonable performance on commodity clusters. It's fairly portable and ubiquitous. And frankly, the best thing you can say about it is if you look at sort of the major advances in HPC over the past decade or so, almost all of the scientific work that's been accomplished has been done in these fragmented or SPMD models. So they have to get a lot of credit for that. At the same time, it's not what I want to be programming in 5, 10, 20, 40 years from now. So there's some big disadvantages. This sort of cooperating executable model of parallelism is sort of a single level of parallelism, and architectures have many levels of parallelism, algorithms have many levels of parallelism. I want to be able to exploit those things. As I mentioned, it fails to abstract away a lot of important architectural and implementing mechanisms. And I think it obfuscates the algorithm with lots and lots of low-level details, which makes your code more error-prone, more brittle, and has referred to MPI often being called the assembly language of parallel computing, because you're sort of managing all the explicit movement of data, much as you would in assembly language, hoisting it out of memory into registers and back again. Okay. Just to kind of wrap this up, so what people use to program today, in HPC, they have communication libraries, there's some shared memory models, there's some PGAS languages, which are kind of a next generation of language that kind of falls in between MPI and Chapel. And so the bad news here, if you have my point of view, is that almost all of these are fragmented or SPMD programming models. With the exception of the shared memory models, their global view, but kind of trivially because they assume shared memory, so they don't have a notion of here and there and expensive and cheap, which is very, very important as you get onto these huge system scales. Okay, so they tend not to scale up as well. Okay, so going back to my main thesis statement, I said that one of the main scalability limiters in these HPC programming models is restricting the programming and execution models. And again, I think this limits the applicability of these programming models to the multiple levels of parallelism that exist naturally in hardware and in software. They expose a lot of low-level implementation mechanisms. For example, MPI says too much about how communication should be done, as opposed to simply saying what should be communicated and or when it should be communicated. And it also, most of the models we have today bind the language too tightly to a particular implementation in hardware. So a lot of people do these things where they have an MPI code for the internode parallelism, an OpenMP code for the inter-core parallelism, and then directives for intra-core parallelism. And so you sort of have these three different programming notations, all of which are talking about parallel computing. I'd rather have a language, and that's what Chapel strives to do, which uses a single notation for parallelism and can map it to any of those levels. And then finally, lack of programmability. Lack of programmability is obviously bad in general, but I argue that if you're going to these really large-scale machines and problems, you're not just going to get great performance the first time you do it. You need the ability to modify your code, experiment with it, try different things, tune it. And to the extent that your programming model makes it really, really hard or frustrating to do that, you're perhaps using the wrong programming model. All right, so let me give you a bit of a language overview now. And I'll break this down by spending a little bit of time on just the base language, sort of the scalar language on which we're building. Then I'll go into some of the parallel features for task parallelism and data parallelism. Jeez. You know, I make my career saying the word parallelism, and I still can't say it. Task and data parallelism. And then I'll talk about some of the locality features we have for reasoning about where you are on the machine. And then I'll wrap up at the end. Okay, so at a very high level, Chapel's design was very intentionally intended to be a block-structured imperative programming language. And the reason for this is that while there might be advantages to functional languages or more declarative languages or other sort of interesting programming models, the fact of the matter is that the HPC community, and in fact the mainstream community, is very rooted in sort of block-structured imperative languages, and so we felt that was an important design theme. We also intentionally decided not to create Chapel as an extension to an existing language. So it's not C plus something or Java plus something. And this frustrates a lot of people because they think it would be easier to learn maybe if we did that. And that may be true, but I think there are a lot of reasons not to do that. One is political. If you choose a C-based language, you maybe turn off your Fortran or Java or MATLAB communities. Another is that parallel programming at these scales is very different than sequential programming. And so taking a sequential language that wasn't designed with this in mind and modifying it is not easy to do. And it also tends to cause programmers to sort of stick to their old bad habits, which maybe made sense in the sequential world, but don't make sense at scale. So instead what we did was look at languages either developed in industry or academia, maybe that caught on, maybe that didn't, and take aspects from those that made sense and try to create a new coherent language out of those. I won't go through this whole list of sort of concepts that we borrowed or learned from previous languages, but again, these slides will be made available to you so you can look over them on your own time. So this is my one slide overview to sort of the base scalar language that we're building on. Syntactically speaking, we're adopting sort of the C, by which I mean C, C++, Java, and to an extent Perl, family of syntax whenever it's possible and useful for us. And this is just sort of reflecting the fact that, by and large, more and more of the sort of new languages coming out tend to fall into this family of syntax. Might as well sort of build on that familiarity. That said, we do have some pretty major departures. Probably the biggest one is our declaration and our casting style syntax uses more of a Pascal or modula-based syntax. There, I think, are good reasons for this. I'm not going to make that argument today, but we could talk about it afterwards if anyone's interested. We also use a pretty different syntax for generics than you would see in like a C++, for example. And our for loop syntax tends to be different as well due to the parallel features in the language. In terms of the main language elements, we have more or less standard scalar types, expressions, and statements. You would find sort of what you're used to finding in most languages. We support object-oriented programming using both value-based classes, more like a C++ style class, and reference-based classes, more like a Java style class. But we very intentionally made this not an object-oriented language, a pure object-oriented language, because we didn't want to disenfranchise the sort of C and Fortran programmers that are today the bread and butter of HPC. So it's there if you want it, and you like it, and you use it, and you don't have to use it if you don't want to. It's not a pointer-based language. We tried to very much restrict the opportunities for aliasing in the language. In fact, the reference-based classes are one of the main ways that you get aliasing in the language. And because of the lack of pointers, we have argument intents, which are somewhat similar to Fortran or Ada, where you sort of talk about copying things in or out or just passing them by const to a function. This last list down here is sort of a grab bag of base language features that I really, really like. And if you asked me to design any other language, I would try to argue to put these in. The first is iterators, and not in the sort of C++ or Java style, but in the Clue or Ruby style, a kind of function that yields values, sort of creating this stream of values coming out of it. The second is tuples. I think tuples are a very simple concept, and they make code so much more beautiful than, for example, a function that can only return one value. We have a latent type scheme, so you can leave off the types of variables, of arguments, of class members. These will be inferred through some fairly simple static rules, so you still end up with a statically typed program, but you don't have to be typing type information over and over again if you're just kind of in an exploratory programming mode. We have a very rich compile time language that allows you to do a lot of compiler transformations in the language. And we have configuration variables, which are kind of meant to solve the whole command line parsing problem. So I actually add command line arguments to my programs, which I never do in C. Okay, so moving on to the parallel features, I'm going to skip through these pretty quickly because I think the more interesting features for scalability are the data parallel features. So let me just say at a high level, this first slide talks about ways that we create parallelism. Begin creates a task, syncs waits on a bunch of tasks to complete. That's all I'm going to say. We have ways of coordinating between tasks. These are in a data-centric manner. We have sync and single assignment variables, which are a way of tasks kind of making sure that someone else has written or read a result. And we have atomic sections, which support transaction against memory, using either hardware or software transactional memory techniques. Vijay will be talking more about transactional memory in his talk later on today. And then we have a few ways of creating structured tasks using sort of a compound statement style co-begin and a loop style co-for-all. So again, I purposely sort of flitted through that quickly in the interest of time. Again, look through these slides. If you have questions, I'd be happy to talk to you about them offline. So let's talk a little bit more in depth about the data parallel features in the language. Chapel, as ZPL before it, has this notion of a first-class language concept that represents an index set. You can think of this as representing kind of the size and shape of an array without representing any of the data that would be stored in the array. So kind of like the silhouette of the array if you were to squint your eyes at it. We have a pretty rich set of these. You can have integer tuple-style index sets, which give you sort of your traditional rectilinear arrays, as well as strided and sparse subsets of rectangular arrays. And then we have anonymous indices, anonymous domains, which allow you to do sort of graph-style computation. And we have domains over arbitrary values, which is kind of more of a hash table or dictionary-style index set. So here I'm doing a domain of indices which happen to be strings. This slide just shows the different declaration syntaxes for these. I declare these, because they're first-class object, I can declare them as variables, name them, give them a type and value. I can reassign them over time. So they really are first-class. One of the main things you do with these domains, of course, is you use them to declare arrays. So here, for example, I'm saying, take my dense domain and give me a dense array where for every index in that index set, I allocate a complex value. Here I do the same thing for my sparse domain, saying for every element there, give me a real floating point value. You can also do this for the graph and dictionary style domains. You can use these domains to iterate over your index set. So I can say for all ij in the strided domain, update the dense array at ij using the sparse array value at ij. So I'm iterating over this index set in the middle, reading from my sparse array, and then incrementing into the corresponding values of the dense array. Again, you can iterate over the, even though I don't show it here, you can iterate over the graph or dictionary style domains and arrays as well. Domains also support a richer notion of slicing than you would see in like a Fortran style language. So I can index into an array using an entire domain, which says, give me that complete subarray of elements and do this computation on those elements. So this is actually the same computation that we saw in the previous slide. And then domains also are a mechanism for reallocating arrays in the language. If you reassign a domain, it causes the array to be reallocated and any overlapping values to be preserved by default. So here, for example, I make my strided domain twice as strided in the column dimension and add in every other element. I add maybe an equator to my sparse domain over here to get new non-zeros along those indices. And the arrays get reallocated automatically for you. Okay, so moving on from data parallelism to locality. We have a notion in the language of a locale, and this is an architectural unit of locality. So it has the ability to store things in memory, to do processing. The idea is that all threads within a locale will have more or less uniform access to local memory within a locale, and remote memory is going to be more expensive. So on a commodity machine, you could think of a multi-core processor or an an SMP node as being a locale. So what do you do with these locales? Well, when you run your program, you specify how many locales you want to run it on. So 8, for example. That'll be passed off to whatever machine manager you're using that'll actually allocate those resources for you. And then within the code, you have access to a few variables that talk about the number of locales, the index space of those locales, and you get an array of the locales, which represent sort of here are the machine resources that you're running on. You can't do a lot with these locales, but it gives you the ability to sort of talk about where things are running and where things should be allocated. Given this sort of initial array of locales, you can then create your own views of the locale set. For example, here I've reshaped it into a 2-dimensional set of locales. Here I've broken it up into 2 disjoint sets of locales that maybe I'm going to run different tasks on. And then we use these on clauses in the language to indicate where tasks should execute. We can do this either in a data-driven manner, saying execute these tasks on the locales that own these elements of the array, or we can name the machine resources explicitly by indexing to the locales array or specifying one of the other locale arrays that I created on the previous slide. So this allows me to steer not only where computation runs, but also where data should be allocated, and lets me worry a lot about locality in my language if I don't trust the compiler and the runtime to do something intelligent for me. The other thing we use these locales for is these domains and arrays that we've been computing on can be distributed across locales, much as they were in ZPL. So here, for example, I can say, distribute this domain D in a block manner to my computational grid, which is this 2-dimensional view of my locales. And that's going to have an implication for how the arrays are partitioned up as well. In addition, it also tells me sort of a default work allocation when I start iterating over this domain or using it to slice arrays, things like that. So these distributions specify a mapping of indices to locales, how each locale should store its local indices and its array elements, and it also tells how the parallel operations on domains and arrays should be implemented. So, what should each core on each node do if I do a for all loop over this locale, over this domain or this array of values? Okay, I'm finding out that I am over time, as often is the case. So let me, let's see. Let me just think about what I'm going to do. So let me tell you what I'm not going to talk about. All of these concepts lead to what we call this multi-resolution language design, which is we want you to be able to program at a high level when it suits your needs and to dive down closer and closer to the machine when it suits your needs. So distributions are a high-level way of programming. On clauses are a very low-level way of programming. We think a language needs to give you both in order to be scalable. To wrap up, I was going to tell you what do we work on from day to day. You could probably guess. I was going to tell you about our prototype implementation and what its status was. You can read about this in your own time. And I was going to sort of talk about how do HPC computations compare and contrast with data center concerns, as I understand it, and pose the question as to whether or not Chapel would be a good data center computation language or not. I think some things are very appropriate, other things would require some new challenges. I'm not an expert in data center computation, so I sort of mentioned here that this could be a potentially interesting collaboration if people are interested in looking at it. If you don't work on data center applications, but something else looks interesting to you, we're open to other collaborations as well. Here's a summary, which I won't repeat. You've probably heard it by now. This is our team, and this is how you contact me if I don't answer your question in the next 5 or 10 minutes. So thanks very much.